Welcome back to QHSE Talks, your source for in-depth explorations into the systems that shape our environment and impact the world we live in. Today, we're diving into something you can't see, can't touch, but depend on every second of your life, the very air around you. Now, that might sound simple, right? Air. But here's the thing. The air we breathe is far from empty. It's a complex mixture of invisible gases, microscopic particles, and chemical reactions happening in real time all around us. And knowing exactly what's in that mix isn't just science for science's sake, it's the foundation of environmental protection, public health, and sustainable development. Because when we talk about ambient environmental monitoring, we're talking about the technology and science that tell us what's really happening in our atmosphere, second by second, molecule by molecule. It's not just about pollution. It's about precision. It's about measuring the unseen, proving the harm, and guiding every environmental decision that follows. Think about it. Every clean air regulation, every emission limit, every national air quality standard, it all begins with data. Without measurement, there's no proof. Without proof, there's no action. And without monitoring, we're flying blind in the very environment that keeps us alive. From sensors that track sulfur dioxide and nitrogen oxides, to instruments that capture microscopic particles called PM₂.₅ and PM₁₀, ambient monitoring gives us the hard evidence, the numbers that reveal when the air around us shifts from safe to hazardous. And this isn't just local, it's global. Across continents, environmental monitoring networks are mapping pollutants, identifying sensitive zones, and feeding the data that helps us model, predict, and ultimately prevent harm to people, to ecosystems, and to the planet itself. It's the quiet heartbeat of environmental protection. Unseen, but absolutely essential, because you can't manage what you don't measure. So today, we're not just talking about air pollution, we're unpacking the entire science of how we know what's in our air, from the philosophy behind clean air to the micro-level particles that challenge it. We'll break down the methods, the metrics, and the meaning behind one of the most important monitoring systems on Earth.
Okay, let's start unpacking this. It sounds like a massive undertaking. When we talk about ambient environmental monitoring, I think, many people immediately think of maybe smog checks for cars or those air quality alerts on the weather report.
Sure, those are the visible parts.
But the scope is actually, well, far, far broader than that, isn't it? You mentioned it's composed of 4 distinct pillars, kind of scientific surveillance working together.
That's right. It's designed to track pollution across all the major environmental matrices, you could say. It's meant to be an integrated system.
Okay. So what are those 4 core components? What makes up the full monitoring program?
Well, the first component, and it's going to be our main focus today, is air pollution monitoring.
Right.
This means continuously sampling and analyzing the chemical and physical composition of the ambient air. And by ambient, we mean the air external to buildings, tracking regulated gases, tracking particulate contaminants.
Okay, air first. What's number 2?
Second, we have water pollution monitoring. So this targets contaminants in, well, everything water-related, rivers, lakes, groundwater, even the oceans. Now, some of the chemicals might overlap with air monitoring. Think about acid rain getting into lakes, for instance.
Good point.
But the physical logistics, the sampling techniques, they're obviously completely different for water.
Okay, so we've covered the fluids, the moving parts, air and water. What about the more static elements of the environment? Does monitoring cover those too?
It absolutely has to. That's component number 3, sediment, soil, and biological monitoring.
Okay. Why is that critical?
Because it reveals the long-term picture, exposure and accumulation over time. Pollutants, they don't always just vanish when they leave the air or water.
Right, they have to go somewhere.
Exactly. They often settle out and concentrate in soil and sediment, and from there, they can really impact the food chain.
Working their way up.
Precisely. So monitoring biological systems, looking at plants, fish, sometimes specific sentinel species that are known indicators that shows the actual effect of maybe chronic low-level contamination that you might totally miss if you only took quick snapshots of air or water quality.
That makes sense. Long-term buildup. And the fourth component, you said it sometimes surprises people who are focused purely on the chemistry side of things.
Yeah, that would be noise level monitoring.
Noise. How does that fit in?
Well, you're right. Noise doesn't really fit the classic definition of a chemical or physical contaminant, like, say, a particle or a gas.
Well,
But it is a significant environmental stressor. Think about quality of life near airports or highways. Think about impacts on animal behavior, communication, stress levels, and human health too, stress, sleep interruption.
okay. I can see that. An environmental stressor.
Exactly. So because it has those measurable impacts, it really has to be included under the umbrella of comprehensive ambient monitoring. It affects the environment people live in.
That really is an all-encompassing system. Air, water, soil, biology, noise. But let's dig into the why a bit more. The strategic objectives. Why are governments, researchers, health organizations globally, why are they committing, well, frankly, massive budgets to these 4 monitoring activities?
Right. The cost is significant.
So what are the specific goals? Our source material listed 6 strategic objectives, the so what, that justifies this constant expensive surveillance.
Yeah, this is really about the operational purpose. Every dollar, every euro spent on setting up a monitoring station or running a lab analysis, it really has to serve one or more of these 6 objectives. Otherwise, it's wasted effort.
Okay, let's break them down. Objective 1.
The first objective is absolutely foundational, mapping the concentration of pollutants in the environment. Before you can do anything else, you have to quantify the problem. You need to know where it is geographically.
Just finding out where the bad stuff is.
Pretty much. This involves creating detailed maps, often using geographic information systems, GIS, showing pollution gradients where concentrations are high, where they're low, how pollution spreads or disperses from sources. This spatial analysis, understanding the where, is the absolute starting point for any sensible policy decision that follows.
So mapping tells us the size and the shape of the contamination cloud, so to speak.
Correct. And that information feeds directly into the second objective. Identification of pollution-sensitive zones.
Okay, how is that different from just mapping concentrations?
This moves beyond just the raw numbers, the concentration levels. A sensitive zone might not actually have the highest concentration of, say, sulfur dioxide in the entire country.
Right.
But it might contain something particularly vulnerable. A protected wetland, maybe. A habitat for a rare or endangered species. It could be a historic marble monument that's highly susceptible to acid rain damage. Or, critically, it could be a densely populated neighborhood with already high rates of respiratory illness, like asthma in kids.
So it's about the impact in that location, not just the level.
Exactly. The goal here is to identify areas where the impact of a given level of pollution is disproportionately high, where the consequences are worse.
Okay, so objective 1 is the quantitative measurement, how much pollution is where. Objective 2 is more of a qualitative risk assessment, who or what is most vulnerable. How does knowing that translate into the physical infrastructure, the monitoring stations themselves?
It leads straight to objective 3, identification of possible sites for monitoring stations. Once you understand where the pollution tends to concentrate, and you know which populations or resources are most vulnerable or sensitive, well, then you know exactly where you need to place your expensive, continuous air monitoring equipment.
Makes sense. Put the gear where it matters most.
You need to gather representative data. That's key. Not just data collected right at the factory fence line, although that's important too. You also need data from the downwind community, where people are actually living and breathing that air day in, day out.
Okay, that covers setting up the data collection. What about using the data? The regulatory feedback loop.
That's objective 4. Tracking progress towards national quality standards attainment and emission reductions. This is really the accountability function of monitoring.
Holding feet to the fire, basically.
Exactly. When a government regulation mandates, say, a 15% reduction in nitrogen oxide emissions across a particular region over 5 years, the monitoring stations are the proof. They must confirm that the air quality is actually improving as expected. If the monitoring data keeps showing continued exceedances of the standard, well, then the regulation isn't working or isn't being enforced properly.
And regulators have to step in.
They have to intervene with stronger measures or figure out why it's not working. The monitoring data is the measurable proof of compliance or non-compliance.
Got it. Okay, the final 2 objectives sound, well, deeply scientific. They seem to link the raw data from the monitors to more complex things like predictive models and even human health outcomes.
They absolutely do. Objective 5 is serving as the basis for modeling of predicted pollutant concentrations in ambient air. Air quality, as you know, is never static. It shifts constantly with wind direction, wind speed, temperature, atmospheric stability.
Right, it's always changing.
So monitoring stations provide those real-time, real-world data points. These act as initial conditions for complex computer models, atmospheric dispersion models. And crucially, the monitoring data is also used to calibrate those models to make sure they accurately reflect reality.
Okay, so the models predict the future based on current conditions.
They can predict future pollution episodes, yeah. This helps authorities issue timely health warnings. Air quality will be poor tomorrow afternoon. Sensitive groups should stay indoors. Or these models can be used to predict the long-term impact of, say, approving a new industrial facility. What will its emissions add to the background levels downwind?
So the real-world monitoring data is used to check and improve the computer models that then let us predict the future, essentially.
Exactly. It's a constant feedback loop between measurement and prediction. And finally, Objective 6, providing input for human health risk assessment studies.
The direct link to people's health.
This is vital. When epidemiologists, public health researchers study the relationship between air quality and public health outcomes.
Like asthma attacks or hospital visits.
Precisely.
Well,
Quantifying the increase in emergency room visits for respiratory problems or cardiac events or childhood asthma rates during high pollution episodes, they rely directly on the concentration data gathered from these ambient monitoring programs.
wow.
This objective is the literal link between the environmental science, the chemistry and physics of the air, and public health policy. It turns parts per billion of ozone into statistics about human lives and well-being.
Okay, that really lays out the why. Now that we know why we measure, let's step back again and look at the fundamental source of the problem itself. We defined air pollution earlier as the presence of these injurious contaminants. But what's actually introducing those contaminants into the air in the first place?
Well, the underlying cause, fundamentally, is the introduction into the air of, let's call them uncharacteristic agents, physical, chemical, or biological agents that wouldn't normally be there or wouldn't be there at those levels. Or it can also be just a significant change in the natural concentration of agents that are normally there. Too much of a normal thing can also be pollution.
Right. I think the key concept here, based on our sources, is the duality of the sources. Pollution isn't just man-made, is it?
No, absolutely not. It results from both natural processes and human activity. Think about volcanic eruptions throwing massive amounts of ash and sulfur dioxide into the air.
Huge natural source.
Or large dust storms, pollens from plants, smoke from natural wildfires. These are all forms of natural air pollution.
But our sources seem to highlight a really critical shift in emphasis here.
Yes, they did. While natural processes have always influenced air quality, sometimes dramatically, the material really stresses the increasingly important role that mankind plays.
Why the shift?
Well, natural systems usually operate in cycles. Volcanoes erupt, forests burn, but then the environment often has mechanisms to absorb or buffer those effects over time. Human activity, however. We often introduce chemicals that are completely novel to the environment, things that don't break down easily, or we release familiar substances at rates that just completely overwhelm the planet's natural capacity to assimilate them.
So we're tipping the balance.
We are rapidly and in some ways fundamentally altering the chemical and physical composition of the atmosphere on a global scale.
And if we had to pinpoint the two most dominant human drivers, the activities responsible for the bulk of the chemical and physical pollution that this whole monitoring system is primarily designed to track and manage. What have they do?
Your sources are very clear on this. They are the twin engines, really, of modern industrialized society. First, the combustion of fossil fuels in the production of electrical energy. Power plants burning coal, oil, and natural gas.
Okay, energy production. And the second?
Second, the emissions from motor vehicles. Cars, trucks, buses, ships, planes, anything burning gasoline, diesel, or jet fuel.
Right.
These two activities release absolutely massive, sustained quantities of what we call primary pollutants. Things like sulfur dioxide, nitrogen oxides, carbon monoxide, and critically particulate matter, text PM₂. These are the main things our global monitoring network spends billions trying to measure and track.
That's a perfect transition.
Yeah.
We move now from the why, the regulatory intent, and the sources to the actual science of the atmosphere itself.
Yeah.
Before we can really understand contamination, I think we first need to appreciate the natural balance. What does the air look like, chemically speaking, when it's clean?
Right, the baseline. If you take a representative sample of natural, dry air, anywhere in the world pretty much, its composition is incredibly stable and consistent. It's overwhelmingly dominated by just three main components.
Okay, what are they?
Nitrogen, chemical symbol text N2, is the most abundant by far. It makes up 78.084% of dry air.
Almost 4/5.
Yeah. Then comes oxygen, text O2, which we obviously need to breathe, at 20.948%.
So N2 and O2 together make up about 99% right there.
Almost exactly. The third most abundant is argon, symbol R. It's an inert gas, meaning it doesn't really react chemically with much. Argon makes up 0.934%.
Okay, nitrogen, oxygen, argon. That's over 99.9% of the air.
It is, which leaves only about 0.1%, 1/10 of 1%, for absolutely everything else. And it's within that tiny fraction, those trace components, that most of the interesting atmospheric chemistry happens, and unfortunately where most of the pollution problems arise.
Wow, it's all in that last 0.1%. Let's get specific about those trace components then, especially the ones we hear about all the time, the ones that function as greenhouse gases.
Right. When we start talking about that last 0.1%, we usually stop using percentages because the numbers get too small. We switch to units like parts per million or parts per billion by volume.
Okay.
So for instance, the most widely discussed trace component is carbon dioxide, text CO2, while technically it's about 0.036% of the atmosphere.
That sounds tiny.
It does. We usually express that concentration as 360 parts per million by volume, ppmv. At least that was its approximate concentration around the time our source material was compiled. It's higher now, of course.
360 ppmv still sounds incredibly small compared to 78% nitrogen.
Yeah.
It really underscores how potent these trace gases must be, molecule for molecule.
It really does. And the concentrations get even smaller for other important trace gases. Take methane, text to 4.2. Its concentration is typically around 1.7 ppmv.
Wow, parts per million.
And then nitrous oxide, text it, often called laughing gas, is even rarer, around 0.31 ppmv.
Okay, so just fractions of a part per million.
Right. But, and this is critical, that huge difference in concentration, thousands of molecules of text 4 molecules, it doesn't mean methane is less important environmentally.
Why not?
Because methane is a much, much more potent greenhouse gas per molecule than carbon dioxide is. It traps heat far more effectively, so even at these tiny concentrations, it has a significant impact on the climate system.
Got it. Potency matters as much as quantity. Though that ozone, text 253, we mentioned it earlier, it behaves very differently depending on where it is in the atmosphere, right?
Right.
It's a key pollutant down here, but essential protection higher up.
Ozone is fascinatingly unique in that way. Its concentration is highly variable depending on which atmospheric layer you're in. Down here in the troposphere, that's the layer where we live and breathe, where all the weather happens, and where ozone acts as a harmful pollutant.
Yeah.
Down here, its concentration typically ranges from 10 to 500 parts per billion by volume.
Billions. That's incredibly low.
It is. But even at those levels, it's enough to irritate lungs and damage crops. Now, contrast that with the stratosphere, the layer above the troposphere. That's where the natural ozone layer exists, the one that shields us from harmful ultraviolet radiation from the sun.
Right, the good ozone.
Exactly. Up there, the concentration is much, much higher. It ranges from 0.5 to 10 parts per million by volume, ppmv. Thousands of times more concentrated than down here.
So the exact same molecule, text 033, is a vital protector in one place and a dangerous pollutant in another.
Precisely. Location, location, location. It determines whether that molecule is a blessing or a threat to life.
Speaking of threat, let's circle back to those trace components and formally define that group known as greenhouse gases. The definition provided in our material is actually quite simple, elegantly simple, but really functional.
It is. A greenhouse gas is defined simply as one that absorbs terrestrial, or long-wave, LW, radiation emitted from the Earth's surface and atmosphere. That absorption is the key mechanism.
Okay, let's elaborate on that a bit for the listener. What exactly is terrestrial or long-wave radiation?
Okay, imagine the sun shining down on the Earth. That incoming solar energy is mostly visible light and ultraviolet light. We call that shortwave radiation.
Right.
Shortwave radiation passes relatively easily through the atmosphere and heats up the Earth's surface, the land of the oceans.
Okay, surface gets warm.
Now, once the Earth's surface is heated, it radiates that energy back outwards, trying to cool down. But it doesn't radiate it back as visible light. It radiates it as heat, or thermal energy. That outgoing heat energy is the long-wave, LW radiation, sometimes called infrared radiation.
Got it. Heat radiating back up.
Exactly. Now, the main gases in the atmosphere, nitrogen, textone, and oxygen, they're basically transparent to this outgoing LW radiation. The heat just passes straight through them and escapes out into space.
Okay.
But greenhouse gases like carbon dioxide, methane, nitrous oxide, and even water vapor, they have specific molecular structures, shapes, and bonds that allow them to absorb specific frequencies of that outgoing LW thermal energy.
They trap the heat.
They trap it, and then they re-radiate it. Some of that re-radiated heat goes out to space, but a significant portion gets radiated back down toward the Earth's surface. They essentially act like an atmospheric blanket, trapping heat and keeping the planet warmer than it would otherwise be, which is good up to a point.
Right. The natural greenhouse effect makes Earth habitable.
Absolutely. The problem arises when human activities release extra greenhouse gases, effectively thickening that blanket too much, trapping too much heat, and causing global warming and climate change.
That's a crystal clear explanation of the mechanism. Okay, now let's apply this chemistry knowledge to pollutants specifically. We need to make a crucial distinction between primary pollutants and secondary pollutants. Why is this distinction so important for regulation?
This distinction is absolutely fundamental, not just to environmental chemistry, but to policy and control strategies too. They are regulated very differently.
Okay. So primary pollutants.
Primary pollutants are, well, pretty straightforward. They are pollutants that are emitted directly into the atmosphere in the exact chemical form that causes the air pollution problem.
So what you measure coming out of the smokestack or the tailpipe is the actual pollutant you're worried about.
Exactly. It exits the source already dangerous, already in its harmful form.
What's the classic example our sources give for a primary pollutant?
The textbook example they use is sulfur dioxide. It's a direct product of burning fuels that contain sulfur, which includes most coal and some heavy oils used in industry and shipping.
Right.
The TeX-SO2 comes straight out of the stack. You measure the TeX-SO2 right there at the source or downwind in the ambient air, and that's the specific pollutant you regulate and try to reduce.
Okay, that makes sense. Direct cause and effect. Now, secondary pollutants. This is where the chemistry starts to get more interesting and maybe more alarming. Because the atmosphere itself becomes part of the problem, like a giant chemical reactor.
That's a perfect way to put it. Secondary pollutants are chemicals that are formed in the atmosphere after the initial emissions have occurred.
It's formed later.
Yes. They result from complex chemical reactions that happen when different primary pollutants intermingle and react with each other, often aided by other atmospheric components like sunlight or water vapor, once they are already dispersed out in the ambient air. So you can try to control the primary pollutant emission at the source, but if the atmospheric conditions are right, the secondary pollutant that forms later, maybe miles away, can actually be even more toxic or more pervasive than the original emissions.
Walk us through the danger of that reaction step. What's a key example?
The classic example provided in the text is smog. Historically, the term smog just meant a mixture of smoke and fog, like the old London pea soupers.
Right.
But modern photochemical smog, the kind that plagues cities like Los Angeles or Beijing, is a perfect example of a complex secondary pollutant problem.
How does it form?
Okay, so you might have nitrogen oxides being emitted primarily from vehicle exhaust.
Okay, primary pollutant one.
And you might have volatile organic compounds, VOCs, being emitted from various sources, maybe industrial solvents, gasoline evaporation, even some natural vegetation.
Primary pollutant two.
Right. Now, neither the text note or the VOCs might be immediately causing a major problem at the exact point of emission or at those initial concentrations. But when those plumes of textone and VOCs mix together in the lower atmosphere, the troposphere, and then they are exposed to strong sunlight, particularly ultraviolet light, a complex series of chemical reactions kicks off. And one of the main products of these reactions is ground-level ozone.
Ozone again, the bad kind.
Exactly. That ground-level ozone is the key secondary pollutant here. And as we said, it's a powerful respiratory irritant, bad for crops, bad for ecosystems.
So the regulatory challenge is?
Challenge is huge. You have to control 2 or maybe even 3 different primary precursors, the textone and the VOCs, just to control one secondary product, the ozone. And that ozone might not even form until hours after the initial emissions and potentially many miles downwind from the original sources. It makes attributing responsibility and designing effective controls much, much harder.
It really sounds like a game of atmospheric whack-a-mole. You manage to reduce textone emissions from power plants.
Right.
But if VOC emissions from traffic or industry are still high and the sun is shining, you might still get high ozone levels forming downwind. The secondary pollution can persist even if you tackle one of the primary causes.
That's exactly the problem. It demands a really sophisticated monitoring system, one that can track not just the secondary pollutant like ozone, but all the key primary precursors, different types of VOCs simultaneously across a whole region to understand the chemistry and target controls effectively.
Okay, let's pivot now and focus on what many environmental scientists consider perhaps the most insidious and direct physical threat to human health floating in the atmosphere. Suspended particles, more commonly known as particulate matter, or PM.
Yes, PM is a major focus globally.
These aren't gases, right? They're microscopic solids or maybe tiny liquid droplets suspended in the air. And they're regulated incredibly intensely, primarily because of their ability to penetrate deep into the human body.
That's exactly right. The reason PM poses such a potent health threat really comes down to its physical nature, especially its size. Our respiratory system, has evolved some excellent defenses, hairs in the nose, sticky mucus linings, the cough reflex, all designed to trap and expel larger inhaled debris like dust or pollen.
Right. The body tries to keep stuff out.
It does. But these microscopic particles, particularly the smaller ones, they can simply bypass those defenses entirely. They're too small to be trapped effectively in the upper airways.
And once they get past the defenses?
Once they penetrate deep inside the lungs into the delicate air sacs where oxygen exchange happens, that's where the trouble starts. They can cause direct physical irritation, but more importantly, they trigger an inflammatory response from the body's immune system.
Inflammation in the lungs.
Yes, and that inflammation doesn't necessarily stay localized. It can become systemic, affecting the whole body. And that systemic inflammation is now understood to be the root cause, or at least a major contributing factor, to the really serious health problems that we monitor for when we track PM levels.
Okay, let's get specific. Our source material listed 7 distinct and, frankly, quite dire health issues that are directly linked to exposure to these airborne particulates. Can you detail the kind of physiological damage they cause, maybe starting with the immediate effects on the respiratory system itself?
Sure. We often see immediate localized effects first, especially during periods of high PM concentration. This includes things like increased respiratory symptoms, more coughing, wheezing, shortness of breath, general irritation of the airways.
Makes sense.
We can also often measure a decreased lung function, even in healthy people, using spirometry tests. Their ability to inhale and exhale fully is temporarily impaired.
Okay. What about longer-term exposure?
Well, chronic exposure, the kind you might get living in a highly polluted city for years, or working in certain dusty occupations. That accelerates lung damage. It's strongly linked to the development of chronic bronchitis, which is a long-term inflammation of the airways. And it's particularly bad for people who already have respiratory conditions. It's significantly aggravated asthma, leading to more frequent and severe attacks.
So definite harm to the lungs. But the truly alarming aspect, I think, the connection that really ties air quality directly to mortality rates, is the link to the cardiovascular system, the heart and blood vessels. How on earth does inhaling a tiny speck of dust or soot end up stressing the heart?
Yeah, this connection wasn't fully appreciated until maybe the last couple of decades, but the evidence is now overwhelming. The primary mechanism is thought to be that systemic inflammation we just talked about.
Okay, the inflammation spreads.
It seems so. Once these tiny particles lodge deep in the lungs, in the alveoli, where the air sacs are in close contact with tiny blood vessels, they trigger that immune response. The inflammatory signals, and potentially even some of the tiniest particles themselves, don't stay confined to the lungs. They can pass into the bloodstream. And once those inflammatory markers are circulating throughout the body, they affect the cardiovascular system. This systemic stress is linked to measurable negative effects on the heart and blood vessels.
Such as? What are the specific heart-related issues mentioned?
The sources list several. It includes increased risk of irregular heartbeat arrhythmias. It increases the likelihood of suffering non-fatal heart attacks.
Serious outcomes.
Very serious. And perhaps most tragically, exposure to particulate matter pollution is a proven cause, or at least a significant contributing factor to premature death, particularly in people who already have underlying heart or lung disease. Their conditions are worsened, their lives shortened, by breathing polluted air.
That's incredibly sobering. The air we breathe is directly implicated in the health and function of our heart and circulatory system.
It really is. The link is undeniable now.
So to really understand this mechanism of risk, how the damage occurs, we absolutely have to understand the physics of the particle itself. This brings us to what you call the crucial science of size fractions.
Yes, size is everything with PM.
Size isn't just a way to classify these particles. You're saying it's the key determinant of their destiny. It dictates both how much harm they do to health and how long they persist in the atmosphere.
Absolutely. The entire environmental regulatory system for particulate matter revolves around particle size, specifically the aerodynamic diameter measured in micrometers or microns. That's Levinol.
Okay.
We classify airborne particles into different size fractions precisely because size dictates how deeply they can penetrate into the respiratory tract when inhaled.
Right. So let's break down the main categories. What's the first size fraction we typically measure?
We usually start with the somewhat larger particles, relatively speaking. This is the coarse fraction. It generally includes particles with an aerodynamic diameter from 2.5 other thermometers to 10 PM.
2.5 to 10 microns.
Right. When we measure this fraction, we call it text PM. The 10 refers to particles less than or equal to 10 micrometers in diameter. This text PM is sometimes called the thoracic fraction.
Thoracic, meaning the chest.
Exactly, because particles in this size range are generally small enough to get past the defenses of the nose and throat and pass into the chest cavity, the thorax. However, they are often large enough that they tend to get trapped in the larger conducting airways, the bronchi and bronchioles, before reaching the deepest parts of the lungs.
So they cause irritation there.
Yes, they cause irritation, trigger coughing, contribute to those general respiratory symptoms like bronchitis, but they often don't make it all the way down to the gas exchange region.
Okay, so text PM10 might be things like common dust, pollen, mold spores, maybe material stirred up by traffic or construction sites. It definitely bothers you, makes you cough, but maybe it's often coughed back out or cleared by mucus.
Precisely. It's certainly not harmless, especially for sensitive individuals, but the site of deposition is generally higher up in the respiratory tract. The level of concern and the severity of the health impacts elevates dramatically when we move to the next size category down.
Which is
the fine fraction universally known as text PM.
The one we hear about most often in air quality reports.
Exactly, and for good reason. Text PM₂.₅ refers to particles with an aerodynamic diameter up to 2.5 microns. So these are significantly smaller than the coarse fraction.
Less than 2.5 microns. How small is that really?
Well, a typical human hair is about 50 to 70 microns in diameter, so text PM₂.₅ particles are at least 20 times smaller than the width of a human hair.
Wow, okay.
And this text PM₂.₅ fraction is often called the respirable fraction.
Respirable, meaning?
Meaning they're small enough to bypass nearly all the defenses of the nose, throat, and larger airways. They travel down deep into the lungs and penetrate right into the gas exchange region, the tiny air sacs called alveoli.
Right down where oxygen enters the blood.
Exactly, and because they deposit there, in that region with a very thin barrier between the air and the bloodstream, this is where the potential for particles or the inflammation they cause to enter the circulation is highest. This is why the risk of those systemic effects, the cardiovascular problems, skyrockets when text PM₂.₅ are high. These are the particles most strongly linked to increased mortality.
Okay, that's text PM₂.₅, but then we reach an even smaller and potentially even more dangerous category. The ultrafine particles.
Yes. These are the ultrafine particles, often abbreviated as UFP or sometimes just UP. These are defined generally as particles being smaller than 0.1 mun or 100 nanometers in diameter.
Smaller than 0.1 microns. That's incredibly small.
It is. To put that into perspective, 0.1 mun is about 1,000 times smaller than the diameter of a human hair. We're talking nanoscale dimensions here.
And why are they potentially the most dangerous?
Well, their risk is believed to be highest for a couple of reasons. First, because of their incredibly small size, they penetrate most efficiently to the deepest parts of the lung, the alveoli. Second, there's growing evidence suggesting that because they are so tiny, they might be more capable of crossing biological membranes, potentially crossing the alveolar wall directly into the bloodstream, or maybe even traveling up the olfactory nerve from the nose directly into the brain.
Wow, straight into the bloodstream or brain.
It's an active area of research, but the potential is there and deeply concerning. Additionally, think about surface area. For a given mass of material, the smaller the particles are, the vastly larger their total surface area becomes.
Right, like powdered sugar versus a sugar cube.
Exactly. And that massive surface area on UFPs means they can potentially carry a larger amount of absorbed toxic chemicals, like heavy metals or carcinogenic organic compounds from combustion, piggybacking on them deep into the body. More surface area equals more capacity to deliver a toxic payload.
That's a frightening combination.
Oh.
Deep penetration and a potentially higher toxic load.
It is. which is why there's increasing scientific and regulatory interest in understanding and possibly monitoring UFPs, even though most current regulations focus on text PM₂.₅, 2.5 months.
Now, this critical distinction, based on size, doesn't just determine the health impact. You also said it fundamentally dictates the atmospheric dynamics, basically, how long these particles stay floating around in the air and how far they can travel from their source. Let's contrast the fate of the bigger particles versus the tiniest ones.
Right. The atmospheric lifetime is hugely dependent on size. Let's consider the larger particles, say those significantly greater than 10 millars in diameter. Think coarse dust, sand, larger pollen grains.
Okay, the big stuff.
For these particles, they are sufficiently massive that gravity becomes the dominant removal force acting on them. They will settle out of the atmosphere relatively quickly due to gravitational sedimentation. We're talking typically on the order of minutes to hours.
So they fall out near the source.
Pretty much. Their atmospheric lifetime is short, maybe hours at most. This means their impact is highly localized. Pollution from a local source, like a quarry, a construction site, or a dirt road kicking up dust, will mainly affect the communities in the immediate vicinity. It doesn't tend to travel long distances.
Okay, big particles fall fast and local. Now compare that to the fate of the smallest contaminants, the text PM₂ particles, the ones that pose the highest long-term health risk.
It's a completely different story. For the smallest particles, let's say those less than 1 monolabors in diameter, which includes most of the highly dangerous text PM₂ fraction, and essentially all of the UFP fraction gravity becomes almost irrelevant compared to air resistance and atmospheric motion.
Too small and light to fall easily.
Exactly. These tiny particles are primarily subject to random Brownian motion, jiggling around due to collisions with air molecules, and they get carried along by air currents, the wind. This allows them to stay suspended aloft in the atmosphere for much, much longer periods. We're talking days to weeks, sometimes even longer for the very smallest ones.
Days or weeks floating around.
Yes. And because they stay airborne for so long, they can be transported over vast distances by weather systems hundreds or even thousands of miles away from where they were originally emitted.
So pollution from one place can affect somewhere far away.
Absolutely. Transboundary air pollution is a major issue, largely driven by the long-range transport of these fine and ultrafine particles, and some gaseous pollutants, too.
If gravity doesn't pull them down effectively, what is their primary removal mechanism from the atmosphere? How do they eventually come out?
Their main removal pathway is being washed out by precipitation rain or snow. As raindrops or snowflakes form and fall, they collide with and scavenge these tiny particles from the air, bringing them down to the surface. This process is called wet deposition. There's also some dry deposition, where particles just randomly impact and stick to surfaces like leaves or buildings, but for the smallest particles, wet deposition is generally more efficient over the long term.
So basically we have to wait for it to rain or snow to effectively clean the air of these most persistent fine particles.
Largely, yes, which means during extended dry periods, especially with stagnant air conditions, fine particulate matter can build up to very high unhealthy concentrations.
It really paints a powerful picture. The biggest particles are a local, short-term nuisance, while the smallest, most dangerous particles are a long-lived, potentially global problem connecting emitters and receptors across vast distances.
That's a very good summary of it.
Okay, before we leave this absolutely crucial topic of particulate matter, let's just quickly solidify the precise terminology that regulators and scientists use in monitoring. We've mentioned them, but let's list them clearly.
Right. Precision is key here. So when you see text PM₁ in a report, that refers to particles with an aerodynamic diameter less than or equal to 10 number. That's the thoracic fraction.
Got it. PM₁.
When you see text PM₂ number, that refers to particles with an aerodynamic diameter less than or equal to 2.5 nanometers. That's the respirable fraction, often just called fine particles.
PM₂.₅, the main one for health alerts.
Usually, yes. Sometimes, particularly in research or more specialized regulations, you might also see text PM₁. That refers to particles less than or equal to 1 demolar. This is sometimes also called the fine fraction, or distinguishes the very finest part of text PM₃.
PM₁, even smaller.
Right. And that size range between text PM₂.₅ and text PM, so particles from 2.5 up to 10, is what's formally referred to as the coarse fraction. Although sometimes people informally use coarse to mean anything bigger than 2.5.
Okay, clear distinctions. And finally, there's an overall term for the whole mixture of the particles plus the air they're floating in.
Yes. That combined system, the suspended particles, whether solid or liquid, plus the gas they're suspended in, usually air, is technically called an aerosol.
Aerosol, like hairspray.
Well, hairspray is one type of man-made aerosol, yes. But in atmospheric science, aerosol is the general term for any tiny particles suspended in a gas. So when a scientist talks about measuring ambient aerosols, they are talking about sampling and analyzing that entire complex mixture of suspended particulate matter in the air. Dust, soot, sulfates, nitrates, organic droplets, all of it together is the atmospheric aerosol.
Okay, we've established the chemical components, the primary versus secondary distinction, and the critical physical dangers, especially of particulate matter based on size. Now let's shift gears and talk about the technical infrastructure and the regulatory framework required to actually manage and hopefully mitigate these pollutants.
Right, moving towards solutions and control.
Let's start with prediction. We touched on modeling earlier. If a regulator needs to understand the potential impact of a specific fixed source of pollution, like a factory smokestack or power plant chimney, they need to be able to model how the pollution plume will disperse in the atmosphere.
Yes, atmospheric dispersion modeling is essential for environmental impact assessments and setting permit limits.
What are the absolutely non-negotiable parameters, the specific pieces of information you must have to accurately define and model the release of pollutants from one of these fixed point sources? Our material listed 6 key inputs.
Yeah, trying to run a dispersion model without accurate input data is basically useless. Garbage in, garbage out. These 6 parameters are crucial because they define not just what is being emitted, but critically, how that emission interacts with the atmosphere right at the point of release, which determines how high the plume rises and where it goes.
Okay, parameter 1.
Number 1 is the most obvious, emission intensity, usually symbolized as text. This is the fundamental input, the sheer mass of the specific pollutant being released per unit of time, usually expressed in units like kilograms per hour or grams per second.
How much stuff is coming out? Got it. 2.
Number 2 is the geometric height of the stack, symbol text row. This is the actual physical height of the chimney or stack structure above ground level. It dictates the initial starting elevation of the plume before any rise occurs.
The physical height. Okay. 3.
3 is the internal stack diameter, symbol text. This might seem minor, but it influences the initial mixing and dilution of the pollutant gas as it exits the stack opening and interacts with the ambient wind.
Okay. 4 sounds important for plume rise.
Yes. Number 4 is the gas exit velocity, symbol text. This is the speed at which the pollutant gas is actually shooting out of the top of the stack. This is critical because it contributes to momentum-driven plume rise. A high exit velocity can physically push the plume higher into the atmosphere, helping it overcome gravity and initial surface wind effects.
Pushing it upwards? 5 must be related.
Very related. Number 5 is the gas temperature at the stack exit, symbol text TDO. This drives buoyancy-driven plume rise. Hot gases are less dense than the surrounding cooler ambient air, so they naturally want to rise like a hot air balloon.
So velocity pushes it up, and heat makes it float up.
Exactly. Accurate plume rise modeling has to account for both the initial momentum effect from velocity and the buoyancy effect from temperature relative to the surrounding air to determine the final effective height of the plume release. That effective height, which can be significantly higher than the physical stack height, is what really determines how the plume disperses downwind.
Okay, that makes perfect sense why industrial stacks are often built so high, and why the exhaust gases are often kept hot. It's all about maximizing that effective release height.
That is precisely the engineering choice, yes. Build it high, keep the exit gases hot and fast. The goal is usually to push the pollutant high enough into the atmosphere to allow for maximum dilution and dispersion before the plume eventually mixes back down to ground level where people might breathe it.
It's a strategy to minimize the local, near-source, ground-level concentrations.
Correct. Though, of course, it often achieves this by dispersing the pollution over a much wider area, potentially trading acute local problems for more chronic regional ones like acid rain or regional haze hundreds of miles away. But the modeling using these parameters allows regulators to predict those downwind concentrations and assess the potential impact on those sensitive zones we talked about back in part 1.
Okay, so we have emission rate, stack height, diameter, exit velocity, exit temperature. What's the 6th required parameter?
The 6th is simply the stack localization, usually given as XY coordinates on a map, like latitude and longitude or a grid reference. This anchors the modeled source to the real world, allowing the model to predict where the plume will actually travel and potentially impact specific sensitive receptors, like schools, hospitals, residential areas, relative to the local topography and prevailing wind patterns.
Got it. Location ties the model to reality. Now, this whole complex structure of monitoring and modeling is ultimately aimed at understanding and controlling a specific subset of the most common and high-impact air contaminants. Our sources highlighted what they called the regulated five, the specific pollutants that typically form the basis for national ambient air quality standards around the world. Let's quickly review them.
Right. Regulatory efforts have to prioritize. You can't regulate everything everywhere all the time. So standards are typically set for 4 key primary pollutants. These are the ones mostly emitted directly from sources.
Okay, the big 4 primaries.
They are particulates, usually regulated as both text PM₁ and 2005-5. Second, sulfur dioxide. Third, carbon monoxide, which is mainly from incomplete combustion, especially vehicles. And fourth, nitrogen, which in this context specifically refers to nitrogen oxides, primarily NO and text NO2, also mainly from combustion processes.
Okay, PM, text NO2, those seem to align well with the major combustion sources we identified earlier, power plants and vehicles.
They do. They are the big 4 direct emissions from burning fossil fuels and biomass.
And the 5th regulated pollutant, you called it the outlier.
Yes, the 5th one that's almost always included in the core set of regulated ambient pollutants is the critical secondary pollutant, ozone, specifically ground-level ozone.
Ozone again. It's fascinating, isn't it, that ozone is the only secondary pollutant typically listed right alongside those primary ones for setting legally binding ambient air quality standards.
It really is fascinating, and it reflects 2 things. First, the widespread and severe health and environmental impacts of ground-level ozone, and second, the sheer difficulty in managing it because it's not directly emitted.
So why regulate ozone directly with its own ambient standard if it's just formed from precursors like TECs and VOCs? Why not just regulate the precursors?
Well, you do regulate the precursors, absolutely, but you also regulate ozone itself for several reasons. You need a measurable standard for ozone in the ambient air so the public and health officials can directly gauge the quality of the air they are breathing against a health-based benchmark. Just knowing precursor levels doesn't directly tell you the ozone risk.
Okay, it's a direct indicator of the harm.
Yes. And also, the relationship between precursor emissions and ozone formation is incredibly complex, nonlinear, and depends heavily on meteorological conditions and the specific mix of VOCs present. Simply controlling precursors, while necessary, doesn't always guarantee you'll meet the desired ozone level. Having a direct ozone standard forces regulators to ensure that the combined effect of precursor controls is actually working to reduce the end product.
I see. So to meet that ambient ozone standard, regulators are effectively forced to impose controls, often indirectly, on the primary TECs and VOC emissions from various sources, industry, vehicles, consumer products that are known to contribute to ozone formation downwind.
Exactly. It becomes a multi-layered regulatory strategy. You have standards for the primary pollutants and a standard for the key secondary pollutant that results from them.
Okay, switching gears slightly, but still on the theme of quantification. Before we even get monitoring data back from instruments in the field, engineers and regulators often need to estimate how much pollution a particular source or sector is likely releasing. This is often done using a calculation based on emission rate. Can you break down that basic relationship for us?
Yes, this calculation is absolutely crucial for things like compiling regional or national pollution inventories, for initial permit applications before a source is built, and for comparing the relative contributions of different industrial sectors. The basic formula is quite simple. Emission rate is calculated by multiplying an emission factor by some measure of activity data.
Okay, emission factor times activity data. Let's define those terms. What's activity data?
Activity data is simply a measure of the operational rate or throughput of the facility or process you're interested in. It's how much activity is happening per unit of time. It could be, for example, kilograms or tons of coal burned per hour in a power plant, or vehicle miles traveled per day in a city, or kilograms of paint used per month in a factory. It's the measure of how much is going on.
Got it. The level of operation.
Yeah.
And the emission factor.
The emission factor is the critical piece that links the activity to the pollution. It represents the average amount of a specific pollutant that is released per unit of activity. For example, it might be expressed as kilograms of textisoios released per kilogram or ton of a specific type of coal burned, or grams of texto emitted per vehicle mile traveled by a certain class of truck.
And where do these emission factors come from? Are they measured for every single source?
Not usually, no. That would be too resource intensive. Emission factors are typically derived from actual source testing data, but averaged across a number of similar sources or processes within a particular industry category. Government agencies like the EPA in the U.S. or international bodies compile extensive databases of these average emission factors for thousands of different source types and processes.
So if I know the standard emission factor for, say, a natural gas-fired boiler of a certain size, and I know how many hours a specific factory runs its boiler and how much gas it burns, the activity data, I can estimate its annual text emissions even if its stack isn't individually monitored 24/7.
Precisely. It allows you to estimate emissions based on known process characteristics and operational levels. It's an absolutely essential tool for high-level regulatory planning, for estimating the total regional burden of different pollutants, and for identifying which sectors are the largest contributors, even without having continuous monitors on every single pipe and vent.
That makes a lot of sense. It scales up local activity to estimate the regional or national impact. Now, all this effort, the detailed monitoring we discussed, the complex modeling, the emission factor calculations, it only ultimately feeds into maybe the highest level concept in environmental law and policy. The attempt to define the overall acceptable quality of the environment through the concept of a permissible environmental load.
Yes, that's the overarching goal.
This sounds quite abstract, though. How does one actually define what constitutes a permissible load in a practical scientific sense? What does permissible mean here?
This is where we really bridge the gap from just measuring chemicals to understanding the ecological and health consequences. A load, meaning the total amount of a stressor, like a pollutant, being put onto an environmental system is deemed permissible if the impact it creates. Well, if it does not result in deviations in the overall status or functioning of the ecosystem that exceed the range of natural expected changes or fluctuations.
Okay, so it has to stay within the bounds of natural variability.
Essentially, yes. If the environment can still absorb or buffer the impact, if it can still regulate itself, if the changes imposed by the human load stay within the boundary of what that particular ecosystem can manage without fundamentally shifting its state or losing key functions, then the load might be considered permissible.
And the consequence?
The consequence of staying within that permissible load is that it avoids widespread undesirable effects on the living organisms within that ecosystem, including humans, and it prevents a permanent degradation of the environment to a state of worse quality.
So the ultimate goal isn't necessarily zero emissions or zero impact, which is often physically or economically impossible,
Right.
but rather aiming for zero systemic decline, maintaining the environment's ability to function and regenerate.
Precisely. You could call it the scientific definition of environmental sustainability applied to pollution loads. Now, the key to actually defining this permissible load for any given pollutant or stressor, which, as the source notes, serves as a crucial basis for both environmental regulation and sanitary hygiene standards, is fundamentally reliant on having extensive, detailed knowledge of the effects.
Knowledge of effects. Effects of what on what?
Specifically, knowledge of the effects produced by various influencing factors on living organisms. You have to understand the dose-response relationship. How much of factor X causes what level of negative effect in organism Y?
And what are those influencing factors that we need to study to be able to define that safe threshold, that permissible load?
Our sources group them into three broad categories. First, there are physical factors. This includes things like excessive heat, noise pollution, ionizing radiation, like from radioactive materials, non-ionizing electromagnetic radiation, like from power lines or transmitters, vibrations, etc.
Okay, physical stressors.
Second, the category we've mostly focused on today, chemical factors. This is where our particulate matter, our gaseous pollutants, TEX, ozone, VOCs, heavy metals, persistent organic pollutants, etc., all fit in.
Chemical stressors.
And third, there are biological factors. This could include things like pathogens, bacteria, viruses in water or air, allergens, or the impact of invasive species disrupting an ecosystem.
Physical, chemical, and biological factors.
Yes. To set a scientifically defensible, permissible load or environmental standard, regulators and scientists must ideally understand the dose-response relationships for relevant factors across all three categories, considering their effects on various species, including, of course, humans, and also considering potential synergistic effects where multiple stressors interact. It's an incredibly complex, research-driven, and time-consuming process.
Okay, we've journeyed through the strategic goals, the atmospheric chemistry, the physics of particles, and the regulatory concepts like permissible load. We now arrive at the absolutely crucial practical step that connects all these different elements. The actual physical gathering of data from the air. This is air sampling.
The bedrock of the whole system, really.
So, fundamentally, what is air sampling in this context, and why is it so indispensable?
At its core, air sampling is simply the process of collecting contaminants from the ambient air in a controlled, standardized way. And the specific purpose is so that we can later identify what contaminants are present and critically quantify their concentration, usually back in a laboratory setting.
It's the physical link, then, between the regulatory need to know what's in the air and the scientific evidence required to provide that answer.
Exactly. Without sampling, everything else, the standards, the models, the health studies, is just theoretical. Sampling provides the actual data about the real world.
Now, given that most of the pollutants we're interested in, especially the toxic ones, are present at very low concentrations in the ambient air, we talked about parts per million or even parts per billion.
Right, often very dilute.
We typically can't just, say, fill a small syringe with air outside and take it to the lab for analysis, can we? That implies that the sampling step usually has to involve some way of concentrating the contaminants of interest.
That's correct in most cases. For the vast majority of air pollutants, the ambient concentrations are far too low for direct, immediate analysis using portable instruments, though those are getting better. So the standard approach requires us to draw a very large, accurately measured volume of air, often hundreds or even thousands of liters, through some kind of specialized collection media over a set period of time.
What kind of media?
It depends entirely on the pollutant you're targeting. If you're sampling for particulate matter, PM, the collection media is typically a filter. Air is pumped through a pre-weighed filter made of materials like quartz fiber or Teflon, and the particles get trapped on the filter surface. Later, you weigh the filter again in the lab to determine the total mass collected.
Okay, filters for particles. What about gases?
For certain reactive gases like sulfur dioxide or nitrogen dioxide, the media might be an absorbing liquid solution contained in a device called an impinger or bubbler. The air is bubbled through the liquid and the gas dissolves and reacts chemically with the solution. The solution is then analyzed later.
Bubbling air through liquid. Okay. Any other methods?
Yes, for many volatile organic compounds, VOCs, or other semi-volatile chemicals, the collection media is often a solid adsorbent material packed into a tube. Common adsorbents include activated charcoal, silica gel, or specialized polymers like 10X. As the air passes through the tube, the target chemical molecules adsorb onto the surface of the material. Later in the lab, you use heat or a solvent to desorb the trapped chemicals for analysis, usually by gas chromatography.
So filter, liquid, or solid trap.
Yeah.
The basic goal is the same, though. Pull a lot of air through something that will grab and hold on to the pollutant you care about, effectively concentrating it from a large volume of air onto a small amount of media.
Exactly. The goal is to collect enough mass of the contaminant on that media to be well above the detection limit of the analytical instrument back in the lab, allowing for a reliable quantitative result. This sampling period might be short, maybe an hour, or could be 24 hours straight for measuring daily average concentrations against regulatory standards.
Okay, that concentration step makes sense for particles or for gases and vapors that can be trapped chemically or physically. But you mentioned earlier, or hinted, that there's a key exception. Sometimes the concentration step is deliberately deferred and we collect whole air samples. What kind of pollutants require this special handling and why?
Right. Whole air sampling is a different approach used for specific situations. It's often required for sampling highly volatile organic compounds, VOCs, things that exist primarily as gases at room temperature and don't easily stick to solid adsorbents or react cleanly in liquid solutions. It's also used for sampling certain chemically reactive gases that might degrade or transform if you tried to collect them on traditional media over a long period.
If you tried to trap them, they might change or disappear before you analyze them.
Exactly. Or they might react with the collection media itself, giving you a false reading. So in whole air sampling, the idea is to collect an actual physical volume of the ambient air itself, preserving its composition exactly as it was at the moment of collection, without trying to concentrate anything in the field.
How do you do that? Just fill a bag?
Sometimes, yes, specialized inert bags, like Tedler bags, can be used for short-term samples. But more commonly, especially for regulatory or high-precision work, we use specialized canisters. These are typically made of stainless steel that has been highly polished or specially treated on the inside, electropolished, to make the internal surfaces as non-reactive or inert as possible.
Ah, fancy metal cans?
Pretty much. They come in various sizes, maybe 1 liter up to 6 liters or more. They are usually evacuated, emptied to a near vacuum in the lab beforehand. Then, in the field, you open a valve and the ambient air rushes in to fill the canister, capturing a snapshot of the air at that specific time and location. Sometimes a flow controller is used to fill the canister slowly over a longer period, like 8 or 24 hours, to get a time-integrated whole air sample.
Okay, so you have this can full of the actual air from the site. Then what?
Then you seal the canister tightly and transport it back to the laboratory. There, specialized analytical instruments, often involving techniques like cryogenic preconcentration, using extreme cold to trap the volatile compounds, coupled with gas chromatography and mass spectrometry, GCMS, are used to identify and quantify the target VOCs or other gases within that whole air sample. The concentration step happens in the lab just before analysis rather than during sampling in the field.
That makes sense. Preserve the sample perfectly, then concentrate and analyze under controlled lab conditions. Now, once that meticulous lab analysis is complete, whether it was from a filter, an adsorbent tube, a liquid impinger, or a whole air canister, you finally have the result, the concentration of the pollutant in the air. How is that result typically expressed? Our sources mention 2 common ways, 2 distinct unit systems, and it's important to know why and when each is used.
Yes, the units chosen depend largely on the physical state of the pollutant being measured, whether it's a gas vapor or a particle, and also on regulatory convention. The first way results are often expressed as using dimensionless terms, which are essentially ratio-based measurements. The most common are parts per million, ppm, or parts per billion, ppb, usually on a volume-to-volume basis, like ppmv or ppbv.
Okay, parts per million or billion. When are those used?
These ratio terms, ppm, ppb, are typically preferred for expressing the concentration of gaseous pollutants in the air, things like carbon monoxide, sulfur dioxide, ozone, nitrogen dioxide, and many VOCs.
Why ratios for gases?
Because the volume occupied by a gas changes significantly with temperature and pressure, expressing the concentration as a volume ratio, volume of pollutant gas per million or billion volumes of air, makes the measurement less sensitive to those variations. It represents the relative abundance of the pollutant molecules compared to the air molecules, which is often what's relevant for gas phase chemistry and for comparing levels across different conditions or altitudes.
Okay, ppm or ppb for gases. What's the second method of expressing concentration?
The second method is used when the absolute mass of the pollutant present in a given volume of air is the critical factor, rather than its relative volume ratio. This method uses mass per volume terms.
Mass per volume, like?
The units are usually micrograms per cubic meter, or sometimes milligrams per cubic meter. A microgram is 1/millionth of a gram, and a milligram is 1,000th. A cubic meter is a standard volume of air.
And when is this mass per volume unit used?
This is the standard, preferred method for expressing the concentration of particulate matter, PM, both text PM and text PM₂.₅.
Why mass for particles?
Because, as we discussed, the health effects of particles are strongly linked to the mass of material that gets deposited in the respiratory system. Regulators set ambient air quality standards for PM in units of test 43 because that measurement provides a direct index of the mass burden that people are breathing in per volume of air inhaled. It links directly back to the dose received by the lungs and the subsequent health risk assessment.
That makes perfect sense. So as a rule of thumb, gases and vapors are typically measured in volume ratios, ppm or ppb, while solid or liquid particles, PM, are measured in mass concentration.
That's the general convention, yes. Although sometimes you might see gas concentrations converted to Text 3 as well, using their molecular weight and standard temperature pressure assumptions, especially when assessing total toxic load. But ppm, pp for gases, and PM3 for PM are the most common you'll encounter in air quality reports.
Okay. This whole extensive logistical effort, the careful sampling using specific media or canisters, the sophisticated equipment needed both in the field and in the lab, the complex analysis to get these precise concentrations, it really is the engine driving compliance and understanding. Yeah. We need to close out this section by really summarizing the absolute utility of this whole process. Why make this huge investment in setting up and running these continuous, often expensive air monitoring campaigns? Our sources listed 7 core needs or reasons for air sampling.
Right. These 7 points really detail the massive return on investment you get from good air sampling programs. They span the entire process from initial problem identification right through to final verification that your solutions are working.
Okay, reason number 1.
First, and most basically, to identify and measure air pollutants. This is the fundamental first step. You have to confirm what specific contaminants are actually present in the air in a given location and determine their concentration levels. You can't manage what you don't measure. This step also ensures that any potentially harmful contaminant found is actually included in the regulatory framework going forward.
Identify and measure. Makes sense. 2.
Second, to monitor personal exposures to chemicals, this moves beyond just the general ambient air quality. Air sampling is absolutely vital in occupational health and safety settings, inside factories or workplaces, to measure the air that individual workers are breathing in their specific job tasks. This ensures that their personal exposure levels are not exceeding legally mandated permissible exposure limits, PELs, or threshold limit values, TLVs, set by health agencies like OSHA or ACGRH.
Protecting workers directly. Okay, 3.
Third, to assess the environmental impact of manufacturing processes or other industrial activities. Sampling the ambient air around a facility upwind and downwind helps determine the real-world contribution of that facility's emissions to the local air quality. This often serves to verify or sometimes challenge the predictions that were made by those plume dispersion models we talked about earlier. It's the ground truth.
Checking the model against reality. 4.
4. To comply with government regulations, this is often the primary driver from a legal perspective. Air sampling, conducted according to strict protocols and often using certified methods, provides the indisputable, documented evidence required by law to demonstrate whether a particular company or a whole region or even a nation is meeting its mandated ambient air quality standards or emission limits. It's the proof of compliance.
The legal necessity. 5.
5. To identify the source of the pollutants. Sometimes you detect a pollution problem, but you don't know exactly where it's coming from, especially if there are multiple potential sources in an area. Advanced sampling and analysis techniques can sometimes help pinpoint the origin. This might involve looking for specific chemical fingerprints, like unique ratios of isotopes, or the presence of specific trace marker compounds that can help fingerprint a contaminant plume and trace it back to a particular industry type, a specific factory, or even differentiate between local sources versus long-range transport from another region. Source apportionment, they call it.
Like detective work using chemistry.
And 6. To evaluate the effectiveness of engineering controls. This is critical for proving that pollution reduction efforts actually work. If a facility spends millions of dollars installing a new scrubber on its smokestack, or putting in an advanced ventilation system, or changing its process to reduce emissions, air sampling, both at the source stack and in the ambient environment, provides the definitive, measurable proof of whether that control technology is successfully reducing emissions and improving air quality as intended. Without sampling, there's no objective way to verify the performance or justify the cost of the mitigation effort.
Verifying the fix worked. And point number 7 in the list seems to just underscore the need for the tools themselves.
Exactly. Point 7 simply mentions that none of the preceding 6 objectives are even possible without having robust, reliable, and often highly specialized air monitoring equipment. This equipment needs to be capable of operating accurately and consistently, often under harsh and varying environmental conditions, temperature swings, humidity, dust. And frequently, it needs to perform continuous or semi-continuous low-level detection 24 hours a day, 7 days a week for years on end. The technology itself is a critical need. #outro.
Well, this has certainly been a deep dive. We've taken quite a journey today, haven't we? Starting from the broad strategic goals of environmental surveillance.
Yeah, the big picture why.
Right down to the almost mind-boggling physics of a submicrometer particle interacting with lung tissue. We've established that ambient environmental monitoring isn't just about air. It's a comprehensive system targeting air, water, soil, even noise.
All driven by that critical goal of defining a permissible load, finding that level of impact that doesn't push the ecosystem beyond its natural ability to cope and recover.
And we really broke down the atmospheric chemistry, didn't we? Highlighting that crucial difference between the stable bulk gases making up 99.9% of the air.
The nitrogen, oxygen, argon.
And that tiny fraction of volatile trace components where all the action and the pollution happens. Critically, we established that vital distinction between primary pollutants, the ones emitted directly,
like Tex O2 from a stack,
and the tricky secondary pollutants like ground-level ozone, which are formed later by complex chemical reactions happening downwind. A challenge that, as you said, demands really sophisticated monitoring and regulatory strategies.
It really does. You have to track the ingredients and the final product.
And then we really zeroed in on that particulate threat, emphasizing again and again that size is destiny.
Absolutely. Size determines penetration depth, atmospheric lifetime, transport distance. Everything.
The smaller the particle, particularly those ultrafine particles below zero point 0.1 micrometers. The deeper they penetrate into the body, the longer they stay in the air, and the higher the potential risk for causing that systemic inflammation, cardiovascular stress, and ultimately premature mortality.
And it's that foundational scientific knowledge about particle size, behavior, and health effects that really drives the whole logistical necessity of air sampling, the need for those size-selective inlets on the monitors, and the complex process of modeling emissions from point sources.
So the essential takeaway here, maybe the key message to leave our listeners with, is that scientific feedback loop that underpins and validates the entire system.
I think that's exactly right. It works like this. The knowledge we derive from fundamental research into particle physics, atmospheric chemistry, toxicology, epidemiology, that knowledge drives the necessity for continuous, detailed, sophisticated air sampling.
Okay, science tells us what to measure and why.
Then, that precise sampling data, the actual measurements from the real world, serves two purposes. It feeds directly into the atmospheric dispersion models, calibrating them and making their predictions reliable.
Improves the models.
And perhaps most importantly, that sampling data underpins the entire regulatory process. It provides the scientific evidence needed to define those health-based air quality standards and to set that ultimate goal, the scientifically defensible, permissible environmental load. It all connects. Research informs sampling, sampling informs modeling and regulation hopefully drives emission reductions, which we then verify with more sampling.
Yeah.
It's a continuous cycle.
A cycle built on evidence. So this leaves us, as always, with one final, maybe provocative thought for you, our listener, to carry forward from this deep dive. We've heard that environmental regulation fundamentally relies on understanding the physical, chemical, and biological factors that produce measurable, often harmful effects on living organisms.
Right, that knowledge of effects is key.
Given that, we really have to continually consider the challenge posed by the sheer accelerating pace of human industrial and technological activity. This activity is constantly introducing new, novel, and often completely uncharacterized chemical agents and physical stressors into our shared environment.
Things we've never seen before or haven't studied yet.
Exactly. So the question to ponder is, what new pollutants, what new stressors are we potentially releasing today from new manufacturing processes, new consumer products, new energy technologies that will require defining, monitoring, measuring effects for, and eventually setting a permissible load for tomorrow? The job of the environmental scientist, the atmospheric chemist, the toxicologist, it seems destined to be perpetual, doesn't it? Always chasing the next emerging threat.
It certainly seems that way. It's a constant challenge to keep science and regulation ahead of, or at least keeping pace with, innovation and its unintended consequences. Until next time, keep digging deeper.